Great to see you in tutorial 4. I hope you had some fun on the way with the other tutorials. This tutorial is called Representational Geometry in OIS, and I want to give you a little more details on some of the issues that I touched on in the intro lecture. And in particular, I want to talk to you about a number of related topics on decoding, distance and discriminability, and biased and unbiased estimators. So let's consider how we might measure discriminability with a linear decoder. Imagine you've done an experiment where you've presented two stimuli to human subjects while measuring their brain activity. And in a region of interest that you're studying in the brain, you've measured a number of neurons. I'm just showing two neurons here for visualization, but you can imagine that we've measured a population of neurons. And there are response patterns here. Each dot is the pattern of response on a single trial to either of these stimuli. So the red dots are responses to stimulus 1, and the blue dots are responses to stimulus 2. And the mean of all of these patterns for a given stimulus, let's call that R1, and the mean response for stimulus 2, R2. So this is the vector population activity pattern. So let's say we wanted to know whether there's information in this brain region about which of these two stimuli has been presented. To test that, we can attempt to decode the stimulus from the brain activity patterns. And if these distributions associated with each of the two stimuli were Gaussian distributions, we could estimate the covariance matrix here, the mean and the covariance matrix, which would define these Gaussians. If we further assume that the covariance is equal for the two stimuli, we get a picture like this here, where these contours are isoprobability density contours. And just looking at this, you can see that on one side, the density is higher for the blue distribution for stimulus 2, response patterns elicited by stimulus 2, and on the left side, the density is greater for stimulus 1 elicited response patterns. And so the base optimal thing to do here for decoding would be for a new pattern to assign it to whichever stimulus-related distribution here has a higher density at that point. And the base optimal discriminant in this case is a linear discriminant. So there is a hyperplane decision boundary here, and that can be implemented by defining a vector that's orthogonal to the base optimal hyperplane decision boundary. And that's called the Fisher linear discriminant. So we could use the Fisher linear discriminant in order to define a decoder and then see how well that works. So we fitted the decoder here to this training set stimuli, and we could check how well this decoder works on the training set. However, the decoder, of course, is overfitted to this training set, so this would likely lead us to overestimate how well we can decode. So this could be an extreme outcome where we might be able to perfectly decode all of the points from the training set, despite the fact that actually there's no difference between the two distributions. And that's what happens in high-dimensional spaces when you fit a decoder, which involves fitting all the weights in this vector W, where you have one weight per neuron. If you have a lot of neurons, you just have so many degrees of freedom that you can end up doing very well on the training set, despite the fact that there's actually no information in the data. So what we standardly do, of course, is the formula for the decoding weights for the Fisher linear discriminant. What we do in this case, of course, is cross-validation. We take a test set where we have measured responses to the two stimuli again, so we have independent data, and then we have two distributions again. If we estimated them from the test set data, we'd get slightly different means, and we'd get a slightly different pooled covariance. So we apply the Fisher linear discriminant that's been estimated from the training set to the test data. And this amounts to projecting the test data patterns onto the Fisher linear discriminant estimated from the training set. So we're dropping all these points onto this one dimension, and then we have univariate data. We have all the data along a single dimension. So at this point, we could impose a threshold on this set of numbers in order to check how well we can decode the stimulus from these patterns in the test set. And that would be a pretty good way of checking whether there's actually any information at all about the distinction between these two stimuli in the brain region that we're looking at. So we could compute the decoding accuracy, and it would involve setting a threshold and then counting how many of these points are on the right side of the threshold. Right? So we like to have high values on the right side for stimulus 2 response patterns and low values for stimulus 1 response patterns. With a threshold, we could count how many we get right. However, we have univariate data here, so alternatively, we might think of just doing a t-test to see if there's any difference between these two distributions in one dimension. So doing a t-test actually would also be a reasonable way of checking whether there is any difference between the two distributions that these stimulus response patterns are drawn from. So linear decoding uses a separate test set to evaluate the discriminability of patterns without overfitting bias. And this is something that I'm guessing most of you are already very familiar with. Now, the new thought is that we can similarly use the test set projected onto the training set linear discriminant to estimate the magnitude of separation between the response pattern means without bias. And this is what we call the linear discriminant contrast, and it's also known as the cross-Nobis estimator. So here's the definition of the cross-Nobis estimator. You will see that this looks just like the Malar-Nobis distance. However, the squared Malar-Nobis distance. However, you got this indication that the two response patterns, Ri and Rj, on the right side are from the test set. That's why it says test there. And when you look at the formula, you'll see that the first two elements here are the W, the weight vector of the Fisher linear discriminant. So we can think of this as the cross-validated Malar-Nobis distance, or we can think of it as the contrast in the test data after projection onto the Fisher linear discriminant. So I want to give a little more intuition from a slightly different perspective on why we get unbiased distance estimates through cross-validation. So let's assume for the moment that the true distance is 0, and we have a multivariate neural response space here. If the true distance is 0, then patterns R1 and patterns R2 are drawn from the same distribution. This could be any distribution. I'm drawing an elliptical distribution here. It doesn't have to be isotropic. It doesn't have to be Gaussian either. So you can draw two patterns here and compute the difference between them, and that would be the response pattern difference in the training set. And then we can draw two patterns again from the test set, and we get a different vector here. Now the key point is if the true distance is actually 0 and the patterns are all drawn from the single distribution here, and they're independently drawn from that distribution, then we're equally likely to get this difference vector between the two patterns, or exactly the opposite distance vector. And when we compute the cross-validated distance, we take the inner product between these two pattern difference vectors, and the expectation of that will be 0 because the two inner products that we get for these two different draws that are equally probable they will cancel out in the expectation, right? So for any possible red arrow here, which is a pattern difference in the test set, the opposite arrow is equally likely. So all these pairs cancel out and we get an expectation of 0. If the true distance is positive, however, we have two different distributions here, and will therefore tend to get an inner product that's positive. So this shows that we get unbiasedness for the case that the true distance is 0. It doesn't show that the estimator will also be unbiased for positive distances. So that's a separate issue, but I hope it gives some intuition about how this bias removal through cross-validation works. So let's consider the bigger picture and let's consider some options for measuring discriminability. The first way of measuring distances that comes to everyone's mind is the Euclidean distance. And this would be a good choice if the noise distributions were isotropic. We've seen that modification and improvement to the Euclidean distance is the Mahalanobis distance, which takes correlated noise into account and works well as long as the noise is Gaussian and there is equal covariance for the different patterns that we're comparing. And we've seen that we can also use decoding accuracy to measure discriminability, and we could, in particular, use the training set decoding accuracy as some kind of indication of how separate two classes are. But we were worried about the bias due to overfitting. You can think of all these three as not cross-validated and thus biased ways of estimating the discriminability. So an alternative is the cross-validated variance of these three. For the Euclidean distance, we could instead use the test set intercentroid discriminant contrast, and this is where we define the discriminant as the vector that is the difference between the two means. We could use that as a discriminant, then project a separate set of test data onto that discriminant and see how well we can decode. And if we can decode significantly, then that would be an indication that there's actually a difference between the two distributions. We can also take the structure of the covariance into account and use the test set Fisher linear discriminant contrast, and that's the Cross-Nobis estimator. And finally, we can use the test set decoding accuracy, and that's a very common procedure in computational neuroscience where people try to decode stimuli from brain activity patterns, and when that's successful, then they conclude that information about the differences between the stimuli must be present in the brain region whose responses have been used for the decoding. So note that these top two choices here are covariance blind, so that makes them a little bit less attractive. These choices on the left here are all positively biased, so they are less attractive for this reason. And these choices at the bottom here are ceiling limited and quantized. So when we compute the accuracy, we have to count how many patterns fall on the right side of the threshold, and that includes a quantization, which gives up on some of the information that's present in the continuous response pattern. So from a statistical perspective, that's not perfectly desirable. And then also the decoding accuracy saturates as two distributions get further and further separated. At some point, you just have perfect decoding accuracy. And then if you move them apart further, you're not sensitive to that anymore. This saturation is also a sometimes undesirable property of decoding accuracy. So I hope that gives some motivation for the Cross-Nobis estimator. This is why we like to use this often in practice. Have fun with the tutorial.